In this video, I am discussing the system design of YouTube, but YouTube is a very large scale system. So I will discuss the major parts of the YouTube like uploading a video and watching a video. So we'll support uploading large videos in the system. We'll see what all complexities we face while uploading a video and while watching or streaming a video. In this video, I have considered only two functional requirements, uploading a video and watching a video. Non-functional requirements, the qualities of the system. Here we have upload and watch large videos. Eventual consistency for uploads. Like if I am uploading a video and it is taking some time to be processed, and after some time it is available for all the customers, so that is fine. Low latency watch, less than 500 millisecond. So 300-400 millisecond is considered real time. We want real time watch even in low bandwidth. High availability. We are not focusing on high consistency in this design. Our system should be highly available. Scalability. As we are discussing about YouTube, this is a large scale system, so we have to design the system in such a way that it's highly scalable. Now here are some scale related assumptions I have made. These are not the exact number, but I have just assumed for this discussion. 100 million daily active users, 1 million daily uploads, 400 million daily watch. Of course, YouTube watch will be more, right? Video watch will be more. Maximum video size of YouTube is 256 GB. So that is the max size of video. Now here quickly I have done few calculations, like 1 million daily uploads means 10 power 6 divided by 10 power 5, that is 10 uploads per second. So that is the TPS. Like YouTube video creation. 400 million watch, that is 400 into 10 power 6 divided by 10 power 5 watch per second. So that is 400 is the QPS, video watch. Here 10 power 5 is the number of seconds in a day. Actually it is 86400 seconds in a day, and I have approximated it to 10 power 5. 1 million daily uploads. Assume average video size is 500 megabyte. So that comes around 1 million is 10 power 6 into 500 megabyte. So that is 500 terabyte. 500 terabyte per day, and that means 500 into 365 terabyte per year. So let's assume 365, we can approximate this to 400, and this comes around 500 into 400, 200 KTB or 200 PB, petabyte. So that is per year, 200 petabyte storage per year. Now let's discuss about the entities. So the main entities I can think about is the user who is creating the videos or watching the videos, the video metadata. We'll see if we need more entities we can add later. APIs, the main two APIs are for uploading and watching. So these are the two functional requirements we have, right? So for uploading, we can assume a post API /video/upload, and it will take the video and video metadata. For watching, get videos, the video ID /watch. So this is very simplified API. We'll soon see these are not the correct APIs. We have to modify our design in a different way. So this is not the final API design. Next, see the high level design of the system. So as we are discussing about a YouTube scale design, the scale is very huge, and of course this is a read heavy system, so reads and writes has to be horizontally scaled in a separate way. So of course I am going for a microservice architecture where I am having one API gateway. We are having one upload service, one watch service. Using the client upload page, users will be able to upload the videos, and using this client view page, users will be able to view or watch the videos. This API gateway will take care of lots of things like authentication, authorization, rate limiting, API routing. So the read request will go to this service, right? So it'll go to this service. So this is the API routing and load balancing. So as currently I have drawn only one service, one instance of the services, but as we will be scaling, so we need to have load balancers. So all this will be taken care of by this API gateway. We can have extra load balancers as well for this service, but this is the simplified design. Now as user will be uploading the videos, this will come to this upload service, and this service will store the videos, the actual raw video frames into this S3 or any other kind of blob storage. So if you are using Google Cloud, so you can use GCS or any other kind of blob storage, and the video metadata will be stored in this metadata database. So video metadata as in the titles, descriptions, tags, who created the videos, and all this data. So this is very simplified design. So let's go to the updated one. So usually the videos are stored in this S3, but we use CDNs. So CDNs are edge cache servers that are located close to the users. So the videos are loaded into the CDN. So when users will view the videos, it will come from the CDN. And here I have shown the video metadatas. So we'll have ID, title of the video, creator, who created, creator ID, description if the video is part of a channel, the tags of the video, and the video URL. The video URL, the full video URL that is stored in this S3 or also in this CDN. So there can be multiple URLs. So we can have a separate metadata table as well for this video URLs. Now our main first non-functional requirement was uploading large videos. So video files are large, so 100 MB to several GBs. So the maximum video size the YouTube supports, that is 256 GB if I am not wrong. So uploading through your app server is not optimal. So it will increase the memory and CPU usage of the server. It will consume the bandwidth. First it has to be uploaded to the servers, and from there it has to be uploaded to this S3 or CDN. If 100 users upload at once, your server must handle concurrent large streams, right? So it adds unnecessary network hops and delays, right? File must go from client to app server, then from app server to the blob storage. So API gateway has a hard limit of payload size of 10 megabyte. So if we are going through this API gateway, we cannot upload a file size that is more than 10 MB. So uploading a video that is more than 10 MB is not possible in this way. So the better approach will be client directly uploads in blob storage. So instead of going through this path, if client can directly upload in this S3. So how it will work? So it's not that easy. So how there are different steps to perform that. First, client has to initiate video upload. So this is a video upload initiation API. So this, let's say slash videos initiate. So it will have the title, description, tags, the visibility, it's a public or private video, the file type of the video before AVI or different other types will be there, the size of the video. If we know the size of the video, we can pass it as a metadata, and we'll soon see like this is kind of required. And the response will be one video ID and the pre-signed URL. So this is the pre-signed URL of the S3 or any other blob storage service. Using this pre-signed URL, client can directly upload the upload the video to this S3. So here we see uh, the request, the first initiate request will go to this upload service, and upload service will store the metadata, and it will get one pre-signed URL from the object storage, and it will pass that pre-signed URL to the client, and client using that pre-signed URL will upload the video. Now here I have also added one status column in this video metadata, because when the first video will be video upload will be initiated, so upload service will create the metadata, right? So the status might be like pending or created, something like that, and when the upload video task will be completed, then the status can be changed to completed. So how the upload service will know when the video upload is completed? So S3 has some notification system using some webhook or S3 notification. The upload service can know about the video upload status, and it can update the status in this metadata table. Now S3 size limit. So we talked about the API gateway size limit, and how the network bandwidth usage will be impacted if we upload the video using this path. Now let's talk about the S3 upload size limit. So if object size is greater than 100 megabyte, you should consider using multi-part uploads instead of uploading the object in a single operation. So so if we are uploading a large file, we should not upload the whole file at a time. So if S3 has this limitation, this off limitation, so we should use this multi-part uploads. It's basically we chunk the videos into small parts and we upload the small parts. So how this multi-part upload works? So how it works is, let's say this is the client, this is the backend, and this is the S3. So let's say client will initiate one upload. So from backend will initiate one create upload request to S3. S3 will return one upload ID, and it will generate n signed URLs. Now what is this in? So if based on the YouTube video size, like the backend can decide how many parts we need. So it will request for that many signed URLs, and all these URLs will be sent to this client. Now using those signed URLs, client can upload the parts directly to S3. So it will not go to backend, it is directly putting in this S3 all the parts separately. After it's done, client will initiate one complete request to the backend, and this backend then will request a success, will send a success request to S3. So in this way, multiple upload will take place. Now this is the full architecture of the upload flow. First, client is initiating the upload. S3 is sending the pre-signed URLs for all the parts and the upload ID. Using that, client uploads all the parts to S3. So this is a multi-part upload. So the responsibility of client here is to create the chunks and then put call with the part number and the upload ID, and this is for directly uploading the part to S3. After all the parts are uploaded to S3, it will initiate the finalize call, and then once we are done, the backend service will store the full video URL to this database. So let's say this is the video URL we have stored. Now our next requirement is streaming large videos. So how the client will see or watch the videos? Using this client watch page, client will view the videos, but should it download the videos using via this upload service? No, right? Because the same complexities will arise, because we'll be using more memory, CPU, more network bandwidth will be wasted, and there is the size limit, of course, via this API gateway, and of course there is like unnecessary this network hops and delays, right, if we go via this upload service. So instead what we can do is we can directly download it from S3. Now, is this also a good idea, like to directly download the file, video file from S3? So why downloading directly is not a good option? So we have to wait for a large video gets downloaded. Consider if the video size is 10 to 20 GB. So the maximum size of video is 250 GB that is allowed in the YouTube. But let's say average YouTube's video size is around 10 to 20 GB. Even in that case, we have to wait for the whole video to be downloaded. Client needs to have that much space available in memory to stream that video, to actually store this much 10-20 GB of data. Wasted bandwidth anyway, because if the user stops midway, the entire file was downloaded for nothing, right? No adaptive bitrate support. Direct downloads are single resolution. So if we want to directly download the files, we can download the video files in a single resolution, right? But it can happen that the client's network bandwidth is not stable, right? So using the adaptive bitrate support, we'll see soon what it is. So based on the network bandwidth, the client can decide like which resolution the client wants. Streaming allows adaptive bitrate support. The quality adjusts dynamically based on network conditions. So based on the network conditions, we'll decide what quality of videos we'll be watching. Without adaptive bitrate support, users on slow networks will face buffering or low quality playback. Because let's say when I started watching the video, my network condition is very good and I started downloading in a very high resolution like 1080p or 4K videos, and after some time my network condition has changed, right? So and it's very poor now, and now if I want to download videos in that high resolution, there will be buffering, so our viewing experience will not be good. No content protection, easy to pirate and misuse, because we are downloading the video, right? It will be easy to pirate or misuse. Limited analytics, because we can't track engagement or ad performance. So the analytics will be limited because we are downloading the whole video, and then let's say we are watching half and then we are closing it. It's difficult to track those kind of engagements, right? Now the better solution we have is HTTP based adaptive streaming, and for that we use HLS, MPEG-, there are different protocols for that. So how it works is videos are split into small chunks like 2 to 10 seconds videos, delivered based on real-time network speed, allow resolution switching without reloading. So based on the network condition, we can change our resolution. We can decide which resolution videos I want to watch. And what are the benefits? First, start, like we don't have to wait for the whole video to be downloaded, so we'll start quickly. Minimal buffering, because we'll be downloading the small chunks, right? 2 to 10 seconds clips, right? So the buffering will be less. Efficient bandwidth use and smooth user experience. So downloading these 2 to 10 seconds videos will not take time, so we will have a real-time experience. Now one extra work we have now is we have to split the original video into small chunks, 2 to 10 second chunks. So let's see here. So from after uploading the videos using this multi-part upload, so we have to again chunk it back, So for that I am using one Kafka topic, and there are lots of chunker workers. So this will take the original videos and will chunk it into 2 to 10-second clips, and all these chunks again it will store back to S3. Now one question can come here is when uploading the video, while uploading the video we are chunking the video in the client side, and all these chunks or parts we are uploading in S3. In S3 we are combining this to create one full video. Then again for the streaming purpose we are creating the chunks, right? So why we are doing this, right? So you see these two chunks, like this client side upload purpose chunks and this streaming purpose chunks are different. So the client purpose chunks before uploading, so this is to optimize the upload experience, so we can have as large parts as possible, right? So this is just to upload upload the video to the blob storage. This chunker, so this is responsible for chunking the video into small clips, right? 2 to 10-second clips. This is to optimize the streaming purpose. So we need different types of chunks in this case. So now so this is the flow for chunking, and from the client we can download this small clips to watch the video. So this is the streaming flow. Now here the whole video URL will be storing, right? We are already storing. We also need to store the chunks, right? So that we see later how we will be storing the chunks and how we will be accessing. Before that, one more thing I have to discuss is the transcoding. So one requirement we had is if the user is having low bandwidth, then also we should not have buffer in while viewing the videos, right? So for that transcoding is important. Transcoding means converting video and audio data into different formats, bitrates and resolutions. So this is one diagram I found for transcoding. So transcoder will convert the videos into multiple formats, multiple bit rates and multiple resolutions. So this is a 1080p resolution for 3 Mbps bit rates. This is 480p 1 Mbps, 360p 900 kbps, 240p 400 kbps. So this is just example. There will be lots of other permutations, combinations as required for different devices, because different devices will have different resolution, bitrates and format support, right? So we need, if we want to support this different types of devices, we need to transcode the original video into all these formats, bitrates and resolutions. Now here comes the adaptive bitrate support. Dynamically adjusting the video quality based on a user's bandwidth and the device compatibilities. So based on this device's compatibility and requirement and the user's bandwidth will decide which option we have to choose. The client will decide which option it has to choose at any point. Common protocols for adaptive bitrate streaming includes this HLS and MPEG-. Now let's talk about this transcoder. Let's draw this transcoder in this design. So we put our videos related data in this Kafka topic, and these are the chunkers, that is reading the original video and creating chunks and storing the chunks back in this blob storage again. These are 2 to 10-second clips. Now these chunkers will also put this chunks details in one more Kafka topic, let's say, and there will be lots of transcoders who will read those chunks from this blob storage and will transcode it in different options. Then all these transcoded chunks it will again store back in S3. So these are the whole video processing part. Now we got lots of chunks for different types of encodings, like formats, resolutions, bit rates, right? So we need to store that informations also, right? So apart from the video URL, we have to store the chunks details also. So this will be kind of a JSON type mapping. I have one example, small example here. So this is just an example and we call this manifest file. So let's say this is the video ID, the title and the streams. So this is resolution, 1080p, bitrate, format, codec, chunks. So these are there are two chunks for this. So this is for 780p bitrate format. There are two chunks. For this 480p 1000 kbps WebM, this option we have these two chunks. So this is just an example. So this kind of manifest file will be created that we have to store. So we can store this in database as well. We can store it in blob storage as well. Actually, the manifest file will be uploaded to multiple CDNs. So, and also all the transcoded chunks will be uploaded to CDNs. The user using the client will download the manifest file, and based on the device compatibility and network bandwidth, the corresponding chunks will be downloaded from the nearest CDNs. So this way, the whole streaming will work. Now, one thing to mention here about this manifest file, it is stored in CDN and also it will be stored in S3. And in metadata DB, we can store the manifest file directly as a JSON. For that, we will be needing one MongoDB type database. But instead of that, we can store the manifest file URL. And we can go for one SQL database that can be sharded properly, or if you want to consider a NoSQL database for scale, we can use a database like DynamoDB. Now let's see the functional and non-functional requirements. Functional requirements are satisfied. Non-functional requirements: upload and watch large videos that we have discussed. Eventual consistency for upload, because we are having asynchronous flow to upload and process the videos, creating the chunks, etc. So the multi-part upload also will take time. So the upload part is eventually consistent. Low latency watch, less than 500 millisecond. So even in low bandwidth. So based on different bandwidth, client will have adaptive bitrate and all, and this is a closer to real-time watch we are having. Next is high availability and scalability. So here we are having multiple instances of the service, and we are using API gateway, which is having the load balancer. So the loads will be distributed properly. We can have extra load balancers as well. So this is not a single point of failure, and the service is highly available. Consider this database that is already, we can shard it or you can go for an NoSQL database. The S3 is indefinitely scalable. Kafka is very scalable, and all these chunker and transcoders, if you're using cloud services, all these are auto scalable. So our system is highly scalable and available. So with this, I think we are done with the system design of YouTube upload and watch videos.